Hey there, good morning team. Chemistry coach coming at you with some ionization energy. Remember, cat here in the mouth. So remember, we're working on properties of atoms and trying to find any trends there are in the periodic table with that, right? Moving down a column or across a row. Do they go up? Do they go down like we did for atomic sizes? And relating them back to electron configurations, electron shielding, orbital penetration, all of that fun stuff. So ionization energy we're going to use a lot because we deal with cations, right? Pretty much every ionic compound has a cation, and sometimes it has a +1 charge like sodium, sometimes a +2 charge like barium or magnesium, or a +3 charge like aluminum, or even higher when you get to some of these weird transition metals. But what is that process? Well, you're separating an electron away from that species, right? Typically, we think of it as a neutral atom, but we could remove an electron really from anything if we wanted to. So how much energy does it take to take that electron and boop, separate it from the nucleus? We looked at that in terms of Bohr's model, where you got n equals 1, n equals 2. Well, if you can get it to where n equals infinity, by definition, that's an electron separated from the nucleus. And you could actually plug in n final is infinity into the Bohr equation and calculate the ionization energy, right? You could. So we want to remove that electron, and we define it as in the gas phase. So it has to be in the gas phase. And typically we're dealing with cations. That's what we're interested in, which would be metals. So commonly we're usually associating it with a metal. We could apply it to nonmetals, but they like to gain electrons, right? We'll talk about that in the next video. So let's say we have some generic metal or any space. Oh, beautiful, Oriole. So beautiful. Okay, anyway, got distracted there. Beautiful blacks and yellows there. So we got a metal in the gas phase, and we remove, pop that electron off to give us a +1 cation, right? Now, we're always, unless otherwise specified, we're talking about the ground state, electron configuration, and we're removing the electron that's easiest to remove, the one that's furthest from the nucleus, that takes the least amount of energy. Remember that analogy, the antelope going, you got the antelope herd, and the lion's going in, it's going, I want to get one of them. It's going to go to the one that requires the least amount of energy to take out, right? The one furthest from the herd, boop, easiest to pop off. Same thing here. If something's going in to take an electron, which one is the easiest to take? I'll take that one. Thank you very much. We call this ionization, we'll use capital I1, right? We took one electron from it. Now we could, as long as there's electrons, and we can keep taking electrons till we strip all the electrons off of there. We're going to find out that becomes a big impediment energetically, and I'll show you why. But we call that the first ionization energy. Pretty simple. Would you agree with me, since electrons are negatively charged, and a nucleus is positively charged, there's an electrostatic attraction there. We could use Coulomb's law if we wanted to. So would you agree it's always going to require energy to separate an electron from the nucleus, because the electron's pretty happy there. Hey, I like that positively charged nucleus. And you want to pull it off, it's like, no, boop, gone. So it's always endothermic. And if you're not familiar with that term, that means it requires energy. Energy has to be put into the species to rip that electron away from it, which means I values, ionization values, are always positive. You'll never see a negative value, always. So what I want to look at is, what if we want to remove another electron? Ooh, it gets weird. And I'll give you some specific numbers too. And then we'll look at some trends and then some calculations. When we're looking at successive electron removal, so something had 13 electrons, we could remove all 13 of them. If we have a big enough laser, you can do anything. Pew, 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 right? So I rewrote that first ionization energy, where we got the neutral metal, or whatever it is, in the gas phase. We're just assuming it's a metal atom, neutral metal atom. Pop an electron off. That's the first ionization energy. We know that's going to be a positive value. We'll look at some typical values in a second. I want you to get the basic qualitative concept here. Now, if we want to take another one out, well, let's bring that +1 metal cation in the gas phase down. Now we got to strip a second electron off. Well, that would be called I2, or the second ionization energy. And we can continue that. I could bring M+2 down, remove another electron in the gas phase to create M3+, plus an electron, to 4 plus, and you can keep going until you're out of electrons. But like I was saying, there's a point where it jumps up so dramatically, it becomes chemically infeasible. It won't happen in nature. There's a certain number of electrons that will lose that's preferable. Anything beyond that, that's kind of not going to happen in nature. You could in a lab if you had enough energy. And we're going to look at those values and why they jump up so dramatically at a certain point, right? Based on, you got it, electron configurations, ha 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 ha. But I want to look at some trends first. Would you agree that it would be a lot harder to take a negatively charged electron away from a positively charged species than it would be from a neutral species, right? Just because of electrostatic attraction. So the second ionization energy is always greater than the first ionization energy, and they're both always positive. So I2 will always be a bigger number. We'll find that'll be in kilojoules per mole. And would you agree that as the cation charge increases, it'd be harder to take an electron from a +2 cation versus a +1? So I3 is greater than I2, and I4 is greater than I3, etc., etc., etc. Hopefully that makes sense. Just simple electrostatic attraction there. Hard to pull a negative particle away from an increasingly positively charged species. Let me put some specific numbers up there, and then we'll look at some trends. Here's some specific values for you, and I want to show you why a lot of these metals have these preferred charge. We've learned how to predict preferred ionic charge from electron configurations, right? They want to be isoelectronic with the noble gas that's nearest to them. But let's look at what happens if they try to break up that noble gas electron configuration. Once it's there at its happy state, it doesn't want to go anywhere else. So ionization energy values are typically kilojoules per mole, right? Based on what's now. They used to use you might still get some people using kilocalories and things like that, but we're going to use kilojoules per mole in this class. And I have a little table for my class. If you want to jump on there, you can print that out. See, kilojoules per mole. And I just put, it's not complete, it's not all of them, but as I read through the literature and I see values and stuff, I'll kind of pop them in there, right? So you can see I1, I2, I3 for that, 3D shell, a lot of the metals. I don't have all the non-metals over there because we typically just use it for metals, right? So we're going to focus over on the metallic side, some transition metals. And you can see these only have 1, these have 2. So it's not complete, right? I'm still, picking up values I see here and there. Sometimes I forget. It's all right. But if I provide that on an exam, you could just read the values straight off of it. Or I'll give it to you, in the problem itself. But I like to provide that so you have to find it and look it up and know whether to use I1 or I2 or I3. So let's take magnesium for a sec. Just kicks and giggles. So we got magnesium right here. Boop, 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 boop. Down in the third shell. We got a neutral atom in the gas phase, losing an electron. First ionization energy, 737.7 kilojoules per mole. That's not chunk change right there by itself. That takes a bit of energy to remove that. And here's the electron configuration, the noble gas core orbital box diagram. So you got the neon core. All right, where'd my periodic table go? So prior to magnesium is neon with 1, 2, 3s2. See that? And that 3s2 subshell's full, so it's going to take a little bit of energy to pop that electron out of there. Bam! And then if we take magnesium +1 with this electron configuration, neon with 1 electron in the 3s subshell, that'd be the magnesium +1 ion. It would love to get rid of that, right? But it still takes energy. So to form the +2 cation, the second ionization energy is 1,451 kilojoules per mole. Right? So even though it would love to become that noble gas, it still requires energy to do it. It makes up for it. We'll find out when we do Born-Haber diagrams in second semester general chemistry. Even though it requires so much energy to create the cation, when you finally bring that cation together with the anion, match made in heaven. There's such a massive decrease in energy of the system by bringing the cation and anion together, especially the more higher charged they are. It makes the overall process energetically favorable, even though it's not energetically favorable, removing electrons. So we'll see that next semester. Now, if we want to take out, so once we do that, we're left with magnesium +2, which has the noble gas electron configuration neon. So it's isoelectronic with neon. That's its happy place. Now, we can still pop one of those electrons out, but it's going to require a tremendous amount of energy. So if you got magnesium +2 in the gas phase, and you want to go to magnesium +3, which we know we don't see in nature, that third ionization energy is 7,733 kilojoules per mole. Look at that massive jump. That's because you're busting up the noble gas electron configuration. That's incredibly unfavorable. It takes a lot of energy to take it out of that happy state. See that? So that's why it prefers the +2, because look at that huge jump. It's like when I go buy coins. If you're into coins, based on the quality, they go from one crappy crap to 70 is perfect, MS 70, mint state 70. So if you want to go from MS 60, mint state 60 to 61 to 62, you can see, there maybe it jumps up $20. It looks a little bit nicer, but there's a point where you get to like what's called like an MS 65, where it's hard to see any scratches or any imperfections with your eye. Like you're looking at diamonds, you can't see it with your eye. Clarity. When you jump from an MS 64 to an MS 65, instead of jumping up $20-30, it might jump up 500 or 1,000, and to go from MS65 to MS66 might jump up 3,000, and you just get these exponential increases in cost to get to the near perfection. Just like if you're buying diamonds, when you're researching cut, clarity, and color, those kinds of things, the clarity, you want to get that next grade of clarity. It's gonna jump up a lot. You want to get that electron out of that noble gas. Oh, it's going to hurt. You're going to pay a lot of energy, and nature doesn't want to do that, so it stays at the Mg2+. You'll see that for all the metals. There's a point where there's a massive increase because you're breaking up that noble gas core. All right, let's look at some trends. Before we get to trends, let's do some math. We haven't done that for a while. So if we know the ionization energies, we can calculate the amount of energy it takes given a certain amount of a species, right? So we'll say a metal in the gas phase. So let's say we want to form some barium with a +2 charge, barium +2, because it's an alkaline earth metal, group 2A, it prefers a +2. So let's say we have 1.90 grams of barium. Let's say we got it into the gas phase already. If we hadn't, we would have to do that. And we want to convert it to barium +2. Well, if you think you can do it, pause it and jump at it. But essentially what we have to do is 2 steps. First, because the ionization energies are different. If you look on the table, the first ionization energy for barium is a lot smaller than the second ionization, right? So barium is 502.6 kilojoules per mole for I1 and 965.2 for I2. So we're going to use those values, but since they're different, it takes more energy to remove the second electron. We have to do this in 2 steps. Calculate the energy to remove the first electron for that amount of barium. Conservation of mass. We'll have the exactly the same mass of the barium +1 ion, and then we got to calculate the energy to remove the second electron, and then add those together. All right. So here's the first step. All right. So let's do step 1, and let's take that barium, neutral barium, and let's remove the electron. That's the first step. So what's the first ionization energy again? 502.6. See it right there? 502.6. That'll be kilojoules per mole. Because the units are given. I put the units up there on the top, so I didn't have to write them in all the boxes, right? So we've got everything we need to be able to do this calculation. You ready? So let's take the starting mass. Now notice that's kilojoules per mole. So whatever amount I give you, we got to get that to moles. Well, just use the atomic mass. That should be pretty simple. So let's take 1.90 grams of barium. Let's look up the trusty dusty atomic mass. Where's barium? Is that, I can't read. Is that 137.33 right there for barium? 137, yep, 137.33. So let's go 137.33 grams of barium per mole, right? So we converted to moles. And now we can use that energy as a conversion factor between amount of barium and the energy it takes to kilojoules, right? And if we wanted a unit other than kilojoules, we could do that conversion as well. So now we know we have 1 mole of barium, and that would require 502.6 kilojoules, right? So grams cancels, moles cancels, you're left with kilojoules, units of energy. We got 3 significant digits, 5 significant digits, 4 significant digits, so we're good to 3. So punch that number out, what do you get? I get 6.95 vertical dash line 36 kilojoules. I'm not going to round that, right? Because I asked for the total energy it takes, right? So I'm not going to round anything until I get to the end. I'm going to have to do the same thing for the second electron, then add them together. So let's do it for step 2. Now this would be much easier if it was an alkali metal. We'd be done because you only remove 1 electron. Woohoo! That'd be no fun, would it? So here we're taking the barium ion with the +1 charge, removing an electron to form the barium +2, which is where it prefers to be. And what was that second ionization energy? 965.2? Is that it right there? 965.2 kilojoules per mole. So I2 is 965.2 kilojoules per mole. And I will provide you those values. You don't have to memorize those values. That'd be a pain. Well, let's do exactly the same calculation. Now we have to make the assumption, right? We have to look at what the atomic mass is, or molar mass of the barium ion. Oh, and we're assuming conservation of mass. We still have 1.90 grams of Ba+. Now, what molar mass do we use? Now, remember, an electron is like 1,800 times lighter than a proton or a neutron. So almost all the mass is protons and neutrons. We're not losing protons or neutrons. We're only losing an electron. Boop! Guess what? Didn't notice. The mass is not going to change. It's still going to be 137.33. Trust me, you'd have to go out to so many decimal places to notice the loss of that electron. It would be irrelevant. So we're going to assume the mass of an ion, cation or anion, is the same as the neutral atom. Good? So we're going to go 137.33 grams of that barium ion per mole of that baby. But now we have a difference. See why we have to do this in 2 steps? The ionization energy is different. This is 965.2 kilojoules for every mole of the barium +1 ion. We have to treat them separately and then merge them back together. So grams of the ion, moles of the ion cancel out. We're left with kilojoules, and then we can add the 2 kilojoules together. We'll be good to go. Watch, we're doing all multiplication here, so we're limited by fewest sig figs. But in the 3rd step, we're going to add these 2 answers together, limited by largest absolute uncertainty or fewest number of decimal places. So 3 significant digits, 5 significant digits, 4 significant digits. I limited to 3. I get 13.353. 13.3. There's my 3 significant digits. 53 kilojoules. Now we can just add those together to get. Good thing it wasn't like a +3 or +4 cation. We have to do every single step, right? So let's add these babies together. So let's take our 6.95, 36 kilojoules there. And let's add the 13.3, 53 kilojoules. We're good at the hundredths place here, or 2 decimals. The tenths place there, or 1 decimal, so we're limited to the tenths place. That's larger absolute uncertainty or fewer decimal places. So we're good to the 1 decimal. I get 20.306. So that's not going to round up. It stays at 20.3 kilojoules of energy. And that's how you do those kinds of calculations. Not too bad. We haven't done math for a while, so that just felt good. Right now we can look at trends. I got that out of my system. When we're looking at trends, right, we're on the periodic table like we did with atomic size. As we're moving down a column or group, how does it change? And we're moving across a period or a row. How does it change? Is there a distinct pattern where we don't even need numbers if we're doing something qualitatively? Hey, which of these would be harder to ionize? Oh, that one, because it, further down or further across or whatever it is. We can look at it mathematically or qualitatively. Mathematically, looking back at some of the wave mechanics, ionization energy is proportional to the effective nuclear charge squared over the principal quantum number squared. So you can see since Z effective is in the numerator, and squared, it's highly, highly sensitive to the nuclear charge. The higher the nuclear charge, the more it pulls the electrons in. Remember, the atom gets smaller, right, and holds on to things more tightly. So it's kind of the opposite atomic size. The smaller it is, right, the higher the Z effective, the smaller it is, the more tightly it holds things off, and the higher energy, more energy it takes to remove it. And then since the N value is in the denominator, the larger the N value, the smaller the ionization energy, which means as you get, here's the nucleus, as you get further and further away, it gets easier to pick that electron off because it's further from the nucleus, right? Which means the bigger the atom, the lower the ionization energy. So as N increases dramatically, ionization energy decreases, okay? This is exactly the opposite trend of atomic size. So you can look at it mathematically, or you can look at it qualitatively, just go, well, the further from the nucleus, the easier it is to remove. So the bigger the atom, the lower the ionization energy. Make sense? And then that'll help us moving down, right? If we're moving across, remember you're in the same N value. So the sizes decrease, go in that direction. So yeah, we could think of it exactly in terms of atomic size. We know atomic size gets bigger going down, so it should be easier to ionize, and size gets smaller going across, should become harder to ionize. Let's see if that makes sense. So the larger the atom, or the higher the N value, the lower the ionization energy. Remember, Z effective, even though you're adding neutrons because of screening, doesn't increase dramatically going down, but N squared makes a huge difference. So N values dominate going down a column. So the larger the atom, the lower the ionization energy, so I decreases going down. So francium should be less than cesium, should be less than rubidium. And here's some numbers to do that. We got lithium, sodium, and potassium. That's all I had room for. So I took these alkali metals, lithium, sodium, potassium. N equals 2, N equals 3, N equals 4. So lithium is smallest, then sodium, potassium is biggest. We would expect it to get easier to move the bigger the atom, which is true. 519.9 kilojoules per mole for lithium, 495.8 kilojoules per mole for sodium, 418.7 kilojoules per mole for potassium. So it gets easier to ionize as you move down. I think that's pretty easy. The bigger it is, the easier it is. Left to right's a little trickier, and there's a few exceptions based on electron configurations. All right, going left to right across a period or a row, we know the N value is the same, right? N is constant, but Z effective is increasing because the electron shielding due to the extra electrons doesn't quite cancel out the increasing number of protons in the nucleus as you move left to right. And you can also see it here. If that's especially constant, Z effective goes up, I is going to go up as well. So as you move left to right across a period, right, N is constant, Z effective goes up. So atoms get smaller. We knew that from atomic size trends, with some exceptions in the transition series. And they're harder to ionize. So we can make the general conclusion, across a row or a period, ionization energies increase, right? So they should be higher over here and less over there. Right? Another reason why nonmetals don't like to form cations. They have really high ionization energies. There are some exceptions. One, we know in the transition series, because you're the electron screening, there's more electron screening because you're adding electrons to the inner D shell. The sizes, the Z effective is effectively constant going across here, so atomic size is relatively constant. Ionization energies are going to be relatively the same going across, with some exceptions. And there's some but special electron configurations dealing with, half-filled subshells, filled subshells being easier or harder to remove versus what you would imagine, where to the point where you could increase the Z effective and it should increase the ionization energy, but it actually decreases because it gives you a more preferred electron configuration. Let's take a look at a few of those to end this. All right, I took the N equals 3 principal energy level, right? So all of these will have N equals 3. So we're looking at the periodic table, 1, 2, 3, right? Going across from sodium to magnesium, jumping to aluminum, silicon, phosphorus, sulfur, chlorine, argon. Brrr. So all on the same N level. So the only difference would be the Z effective, right? Well, we're going from 11 protons to 12, 13, 14, 15, all the way to 18. So obviously, we have more protons in the nucleus. The shielding isn't that great when they're in the same N level, so Z effective is increasing and the size goes down, right? Because it's pulling all those electrons in tighter. And it's holding them tighter, so ionization energy should go up. Well, 495.8 kilojoules per mole for sodium. It gets smaller, goes up dramatically up to 737.7 kilojoules per mole, right? And then aluminum should go up, right? Z equals 13, but no, it went way down to 577.6. That's like, what? What happened there? And then silicon with Z equals 14 then continues the trend to 786.5. So see that trend? So aluminum seems weird. Something's fishy. We're going to have to look at the orbital box diagram for that one. And then we jump to 14 protons with silicon, like I said, 786.5, jumps up to 1,012 kilojoules per mole for phosphorus. Oh, wait a minute. It went down to 999.6. We'd expect it to go up because the Z effective went up, but that one's out of order, so something funky with that electron configuration. And then up to 1251.1 for chlorine and skyrockets to 1520.5. So why is argon so big? It's got a complete shell. So trying to break up or bust up noble gas core electron configuration, as we found out when we did magnesium earlier, requires a tremendous amount of energy. It doesn't want, you could if you had a big enough laser, but that's too much in nature. It's not going to happen. That's why noble gases are so noble. You find them by themselves. They don't react with things in nature unless it's under some really extreme circumstance. Like, I don't know, I've never studied noble gases in lightning bolts, right? Maybe. So let's take a look at these two exceptions. Why did aluminum drop when we wouldn't expect it to? And why would sulfur drop when you wouldn't expect it to? Let's do aluminum first. Do me a favor, draw the electron configurations for aluminum and silicon and magnesium, all right? The orbital box diagrams, noble gas core. All right, let's take a look at the why does aluminum drop down? You'd expect it to be higher than magnesium and lower than silicon if you follow the Z effective trend. Well, here's the noble gas core orbital box diagram for magnesium. So you got the neon core with a 3s sublevel filled. Aluminum has the neon core, 3s sublevel filled with a single electron in the 3p. And silicon is the same thing, but it has 2 electrons. So I drew the electron in red, which is the one that goes bye-bye, right? That's the easiest one to remove. So take a look at the trend. So we have 12 protons, 13, 14. We expect the values to go up, and that's true between neon and silicon, but it's not a huge jump, and there's a reason for that. When you only have a single electron left, it's a little easier than you'd think to get to an empty subshell, but especially a 3p versus a 3s. Remember, the 3p is a higher energy sublevel than the 3s because of orbital penetration. This shields that one out. So, Deathmatch 2000, easier to remove a 3p than a 3s, right? But you've got the increasing Z counteracting that. So it's harder to remove because you're increasing the number of protons, but easier to remove because you're in the 3p subshell. So what happens is removing the last electron from the p subshell is way easier than you would anticipate because it's such a higher energy sublevel than the s, right? So it drops quite dramatically, more than you would anticipate. But silicon it jumps up dramatically for the next one because you've now gone up another proton. So from magnesium to silicon, you've dramatically increased Z effective, even though it might be a little easier to remove a 3p than a 3s. There's just too many more protons in there. So now Z effective starts to dominate. It just has to be that last electron there. So you see that true with aluminum. And if we look on a periodic table, you would probably expect the same thing with gallium versus that, indium versus that, right? You start to see these kinds of trends on the periodic table. So let's look at the last one and we'll be out of here. All right, let's take a look at the phosphorus. Oops, I forgot to label this. Sulfur, chlorine, and anything in the same trends. Whoop. We want the periodic table, not the ionization energy. So if you look at the phosphorus, sulfur, chlorine, same thing with arsenic, selenium, bromine. You see that it should increase, but it drops and then increases again. And you see that trend happens because of the electron configuration. So let's look at it. So phosphorus has 15 protons, sulfur 16, chlorine 17. So Z effective is increasing, size decreases. We would expect ionization energy to go up. But it goes from 1,012 and drops down a little bit to 999.6 for sulfur and then pops up way up for chlorine. So you see the trend there, but sulfur is an exception. That happens in that whenever you have a 4th electron in the p subshell. And this is why. See that last electron for phosphorus? It's got a half-filled subshell. That's symmetric. It kind of likes that. So it doesn't really, it takes a lot of energy to get rid of that. But here with sulfur, you see that last electron is paired up in there. So there's two factors here. One, if we get rid of that, we create a symmetric half-filled subshell. Hey, that's happier. So just for that reason, that'd be easier to move than that one. And two, you remove the electron-electron repulsion energies, because to put two of them in an orbital, you've got they're both a negative. So there's a pairing energy that's you don't have to worry about. So removing a paired energy is easier. A paired electron is easier than an unpaired one in that scenario. And you're creating a half-filled subshell. So even though Z effective goes up, those two factors make that electron right there way easier and requires less energy than you would think. But when you get to chlorine, removing that, yeah, it removes the pairing energy, but you're not creating a half-filled subshell. And you've gone up 2 protons, so it's not enough to override the increasing effective nuclear charge. So it pops up again. There you go. There's ionization energy trends, my friends.